Okay, in this last video for this section, we're going to be talking about parabolas as conic sections. We've talked about parabolas many times, but this time we're going to talk about it as a conic section. So you can see up here in the graph that I have a picture of a parabola, but probably in a viewpoint you've not seen before. You see the vertex here at the bottom, like you're used to seeing, but you see a focus point which is inside the arm of the parabola being hugged by it, and below it you will see a directrix line. You should also notice that the distance between the directrix line and the vertex is called A, or sometimes books will call it P, and the distance between the vertex and the focus is the same distance A, or again, some books will call it P, as I believe your book does. You'll also notice that if you were to draw a line through the focus that was perpendicular to the line through the focus and the vertex, this line is similar to the minor axis on an ellipse, similar to the conjugate axis of a hyperbola, in that it is perpendicular to the primary axis, the major axis, which goes through the focus and the vertex. This one right here, this blue line, has a very weird name. It's called the Lattice Rectum. I know it makes students laugh, but that is what it's called. And the Lattice Rectum connects the two sides of the parabola through the focus point. The distance on each side is the same amount. So from the focus to the edge of the parabola is 2a, from the focus to the other edge is 2a, which means that since this is 2a, this part makes a perfect square, and this part makes a perfect square, so that the whole thing is making a rectangle of length 4a and height 2a. Now let's take a look at some of the notes for this section. Now I have most of these already written out, and I hope that you can read them. The definition of a parabola is the set of all points P, x, y in a plane that are the same distance, equidistant, from a fixed point F as they are from a fixed line D. F is the focus and D is the directrix. So in other words, let's take a look back at our picture. One way of thinking about a parabola is that the distance on the parabola, from anywhere on the parabola, take any point and draw a line straight to the focus, go back to the point and draw a line down to the directrix. For a parabola, those distances are exactly the same. So in an ellipse, you add the distances and there are constants. For a hyperbola, you subtract the distances and they're a constant. But for a parabola, they are the same distance. So again, if I were to take this point right here and I were to measure it straight across to the focus, my distance would be 2a. If I measure from that point straight down to the directrix, the distance is 2a. So in a parabola, the distance to the focus and the distance to the directrix from any point on the parabola is the same. Now let's take a look at another picture. So what I want to do is I want to draw a picture for you, and I want to explain how we're going to graph these. So if we're looking at a graph and we're trying to figure out whether or not it's a parabola or a circle or an ellipse or a hyperbola, how do we know? Let's look at this equation. We have y squared plus 12y equals negative x plus 1. First off, notice that while I have a y squared term, I do not have x squared. So it cannot be a circle, it cannot be an ellipse, it cannot be a hyperbola. This must be a parabola. How are we going to put it into a working form? Now the standard form, again, would be everything on one side, 0 on the other. But the standard general form is not very useful for graphing. So we're going to do the same thing we did previously when we looked at circles, ellipses, and hyperbolas. We're going to complete the square. But in this case, the only square I have is y squared. So I cannot complete the square on x. So I'm going to leave the x where it is, and I'm going to complete the square just on the y as it is. The coefficient here on the y squared is already 1, so I don't need to factor it out. I simply need to compute my b over 2a for the y variable. b is attached to y, so it's 12. And my a is not written, so it has to be an understood 1. And that tells me that I have 12 divided by 2, or 6. So when I factor it, I'm going to get y plus 6 in parentheses squared. Now, what do I need to add here next to it to make it factor this way? How can I complete that perfect square trinomial? I need to square the b over 2a, and that would give me 36. So I need to come up here, and I need to add 36, and I need to subtract 36. So I'm going to have y squared plus 12y plus 36 minus 36. If I add 36 and subtract it, I haven't really changed the problem, although I have changed the way it looks. The first 3 with the plus 36 will always factor into that y plus 6. Now, what about the minus 36? I still have the minus 36 here, but I'm going to move it. I'm going to move it to the other side of the equation to get it away from the squared thing. So we're separating squareds from non-squares. So when I add the 36 to both sides, I end up with y plus 6 quantity squared equals negative x plus 37, which seems like an awfully large number and might be a little bit hard to graph, but that's where it is. Now, in order to complete the graph, in order to put it into full working form, I need to remove the leading coefficient off of the x term as well. And that means that I need to rewrite the right-hand side so that it looks like negative times x, and if I pull the negative out, it also comes out of the 37 and leaves behind a negative 37. Now, when you look at an equation like this, if you have y squared, it cannot be opening up and down because up and down is x squared. Y equals x squared opens up, y equals negative x squared opens down. So if I have y squared instead of x squared, this must open left and right, or left or right. In this case, because I have a negative here, the y is going to tell me it will open left or right. And because I have a negative right here, that negative then tells me that it must open left. So where is my vertex? We don't call it a center. We don't have a center on a parabola, but we do still have a vertex. So where is the vertex? The vertex is where the center was for the circle, the ellipse, and the hyperbola. It is h, k, just as it was for the others. So the vertex is at 37, negative 6. Now, if the vertex is at 37, negative 6, what is that value that when we saw the other picture, that was the A? So let's take a look at that picture again. Remember, A is the distance from the vertex to the focus or from the vertex to the directrix. So how would I find that A? Let's go back to our notes. When I'm back at the notes, the A can be found from the coefficient in front of the non-squared term. So because it's the y that's in the binomial square, it's the other side that will give me the A or the P value depending on your textbook. So in this case, the number out in front of the parentheses was a negative 1. So I'm going to have that the absolute value of 4A, or your book again may call it P, this would be the absolute value of negative 1. In this case, this implies that 4A or 4P has to be 1. That means that A is 1, 4. that means that the vertex and the focus are extremely close together, and they're also extremely close to the directrix. From the focus to the vertex is 1/4. From the vertex to the directrix line is 1/4. But the length of the lattice rectum, which again is the part of the graph that connects across through the focus, similar to the minor axis, that is actually the value of 4a. So that one is a length of 1. Now let's take a look at another example that will be a little bit easier to graph. Suppose that after completing the square, you have this equation. Because you only have one variable being squared, it has to be a parabola. Because it is x that's being squared, this then has to open either up or down. So up or down, like the normal parabola we're used to seeing. Then I look at the sign of the number in front of the opposite side. This one is positive, so that means it has to open up. So now I know that the parabola is going to open up, and I can find the vertex by looking for HK. The vertex is the opposite of the constant next to the variable x, so this would be -4. And it's the opposite of the constant next to the variable y, so this would be -2. And now I need to find out what the distance is between the vertex and the focus and the vertex and the directrix. In other words, I need to find that a or p. So the constant in front of the non-squared variable term is 16. So I'm going to write 16 is equal to 4p, or 4a. And this means that the length of the lattice rectum itself is 16, but it also then means that p has to be 4. So let's put this on a graph and graph it. So this time I've elected to let each square represent one unit on my graph. So when I'm looking at this, I'm going to graph the vertex first, which is at -4, -2. And this is actually on the parabola, so I can go ahead and put a ball at -4, -2. Because it was x that's squared, I know it either opens up or down because this is a function, right? So it's a function if x is squared. It's not a function if y is squared. So this is going to be opening up because the coefficient of the opposite side was positive. So I know it has to look something like this. The question is, where's the focus point? The focus point has to be a distance of 4 away from the vertex on the major axis, which is the one that goes through the vertex and the focus. So it's along that line of symmetry. So I'm going to come up 4, 1, 2, 3, 4. This is where the focus point is. Now the focus point is not a point on the parabola itself, though it's very important to the parabola. So I don't put a ball, I just put an F. Now how can I draw the rest of it? We're used to graphing parabolas a different way. This is another way of looking at them. What we're going to graph is the lattice rectum. Now let's look back at that other picture so that we can see what the lattice rectum is again. If we're looking back here, the lattice rectum is this solid blue line that goes across the parabola through the focus, which is the midpoint of the lattice rectum, and it's perpendicular to the line of symmetry. So that's the line we're looking for. It has a length of 4a or 4p, depending on how your text calls that distance between the two. So now let's go back to our graph. And on my particular graph, that 4p distance was 16, which is whoppingly large, but that means that the whole distance of the lattice rectum, that should be 16. If I'm going to split it in the 16, and again, let's take a look at that picture real quick so we can see what it looks like. The whole distance across is 16, so the left half is 2a and the right half is 2a, which means in my case it's going to be 8 across each one. So counting from the focus, 1, 2, 3, 4, 5, 6, 7, 8, that is on the parabola. and 8 to the left. 1, 2, 3, 4, 5, 6, 7, 8. That's on the parabola. And then I connect these as best I can, and I try to make it look like a parabola. And the lattice rectum is this distance that is going through the focus and is perpendicular to the line of symmetry which goes through the focus and the vertex. Now, where's the directrix line? Well, the focus is 4 above the vertex. The directrix has to be 4 below it. So 1, 2, 3, 4, and it has to be, like the lattice rectum, perpendicular to the line of symmetry or the primary axis. And that's the parabola.